Picture a sealed steel box on the table in front of you. Put your hand on the lid. Don't open it yet. Inside that box, you have been told, is a cat that is somehow alive and dead at the same time, smeared across both, waiting for your eyes to decide its fate. You've heard this 100 times. It's the go-to proof that reality is strange, that nothing is real until you look, that the universe runs on your attention. Here's the thing. The man who built that box would be furious with you. Erwin Schrödinger did not invent this cat to show you how wonderful and mysterious quantum mechanics is. He invented it to make quantum mechanics look ridiculous. The cat was an insult. It was a joke with a target, and for 90 years the world has been laughing at the punchline while completely missing who it was aimed at. So let me show you the story nobody tells, what Schrödinger actually meant, why he was half right and half wrong, and what physics can now say about that cat that Schrödinger himself would have given anything to know. Keep your hand on the lid. We'll open it together, and I promise the truth is stranger and calmer than the myth. This is the physics storyteller. Let's give the popular version its fair hearing first, because it's not stupid, it's just been sanded down until the meaning fell off. The story you know goes like this. Quantum objects, we're told, can be in a superposition in two states at once. An electron can be spinning up and down together. A photon can go through two slits at the same time. Fine. Now, says the story, imagine we hook a quantum coin flip up to a machine that can kill a cat. Radioactive atom decays, cat dies. Atom doesn't decay, cat lives. Since the atom is in a superposition of decayed and not decayed, the cat gets dragged into a superposition too alive and dead, and stays that way until a conscious observer opens the box and collapses it into one answer. And from there, it slides into the version you really absorbed, the one on the poster. Reality doesn't exist until you observe it. Consciousness creates the world. You are the magic ingredient. Look, and the universe picks a lane just for you. And look at where that poster leads once it leaves the physics classroom. It becomes the sales pitch for a whole industry. Manifest your reality, because quantum physics says observation creates the world. Quantum healing. Vibrate at the right frequency and bend the universe to your will. Every one of those pitches leans on the same borrowed authority. The cat, the idea that at the deepest level of reality, your mind is the thing that makes things real. It sounds humble and cosmic at the same time, and it sells a lot of books. And it is, as we're about to see, close to the exact opposite of what the physics actually says. That's why getting this cat right isn't pedantic. It's the difference between a universe that answers to evidence and one that answers to whoever wants your money. I want to be careful and fair here, because there is a real idea buried under that poster. Superposition is real. Measurement is genuinely one of the deepest unsolved puzzles in physics. We'll get to how unsolved. Serious people have argued for decades about what observation means, and I'm not going to pretend that argument is over. But the popular story takes a scientist's criticism of an idea and sells it back to you as the idea itself. It's like finding a comedian's savage parody of a bad movie, cutting out the laughter, and screening it as the movie's official trailer. That is almost exactly what happened to Schrödinger's cat. Don't take my word for it. Let's go back to 1935 and read what actually happened, the letters, the paper, the exact words. Because once you see where this cat was born, you can't unsee it. The cat did not come first. A fight came first. In May of 1935, three physicists, Albert Einstein, Boris Podolsky, and Nathan Rosen, published a short, devastating paper in the journal Physical Review, volume 47, page 777. The title was a question dressed as a grenade. Can quantum mechanical description of physical reality be considered complete? Their answer was no. Not wrong, incomplete. Einstein's team argued that if you take quantum mechanics at its word, it forces you into a picture where two particles, once they've interacted and flown apart, stay mysteriously linked. Measure one, and you instantly seem to fix the state of the other, no matter how far away it is. Einstein hated this. He called that flavor of connection spooky. To him, it was proof that the theory was missing something underneath hidden gears we hadn't found yet. This landed on Erwin Schrödinger like a match on dry grass. Schrödinger had helped build quantum mechanics. The central equation of the theory literally has his name on it. But by 1935, he was deeply uneasy about what his own equations seemed to be saying about reality. The EPR paper put his unease into words, and he wrote to Einstein almost immediately, What followed was one of the great letter exchanges in the history of science, two of the smartest people alive, trading worries about whether the world made sense. And there's a receipt here that matters, because it's the deepest one in the whole story. That mysterious link between two separated particles, the thing Einstein called spooky Schrödinger, studied it hard that same year, and he gave it the name we still use. In a 1935 paper in the Proceedings of the Cambridge Philosophical Society, he called it entanglement, and he did not call it a curiosity. He wrote that entanglement is, quote, not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Sit with that. The man who is about to build a joke to attack the theory is, in the very same breath, telling you that the strangest thing in it, entanglement, is the most important thing in it. He wasn't a crank throwing rocks. He was the theory's own architect, worried about the building he helped raise. The other giant in this fight was Niels Bohr, the leader of what would later be called the Copenhagen interpretation, the mainstream view that quantum mechanics is complete, that it's meaningless to ask what a particle is doing between measurements, and that the crisp classical world simply appears when a measurement is made. Bohr had already fired back at the EPR paper, in the very same journal, insisting the theory was complete, and Einstein had smuggled in an assumption that didn't hold. And notice the name itself, Copenhagen, wasn't even coined until the 1950s by Heisenberg, looking back. These people were not handing down commandments from a mountain. They were arguing, in print, in real time, about what their own equations meant. The cat walked straight into the middle of that argument, and here's the detail that changes everything. The cat wasn't Schrödinger's idea first. It was Einstein's in cruder form. On the 8th of August, 1935, Einstein wrote back to Schrödinger with a homemade thought experiment. Forget particles for a second, he said. Imagine a pile of gunpowder that is chemically unstable over the course of a year. It has a 50-50 chance of spontaneously exploding. If you apply the quantum formalism honestly, Einstein pointed out, then after a year the equation describes the gunpowder as a blend, a smeared mixture of already exploded and not yet exploded. And that, Einstein said, is nonsense. There is no in-between state for a keg of gunpowder. It has blown up or it hasn't. The math is describing something that cannot be. Schrödinger loved it, and he sharpened it. Because gunpowder is dramatic, but it's a little abstract. You can imagine partial burns, smoldering, degrees of explosion. Schrödinger wanted something with no middle ground at all. Something alive. Something you could not talk your way out of. He put the finished version into a 3-part paper, published that autumn in the German journal Naturwissenschaften, The Present Situation in Quantum Mechanics. And in section 5, he introduced his upgrade to Einstein's keg with a phrase that the myth always leaves out. In the original German, he wrote that one can construct ganz burlesque Fälle, quite burlesque cases, quite ludicrous cases. Burlesque, ludicrous. That is the author, telling you in his own words that what comes next is meant to be absurd. He is not unveiling a wonder. He is setting up a farce to prove a point. And then he describes the box you know. A cat, sealed in a steel chamber. A tiny bit of radioactive material so little that in 1 hour, maybe one atom decays, maybe none. Genuinely 50-50. A Geiger counter waiting to catch that decay. If it fires, it trips a relay. The relay drops a hammer. The hammer shatters a small flask of hydrocyanic acid, prussic acid, a lethal poison, and the cat dies. If no atom decays, the flask stays whole and the cat lives. Seal it. Wait an hour. And notice how carefully he built the trap, because this is the part that makes it airtight. He didn't start the chain with a coin flip or a dice roll. Those only look random. Underneath, they're ordinary physics you could predict if you knew every force. He started it with a single radioactive atom, because radioactive decay is the one link in the chain that is genuinely, irreducibly quantum. There is no hidden clockwork inside the atom ticking down to the moment it decays. As far as our best physics can tell, whether it decays in the next hour is not merely unknown to us, it is undecided by the universe itself. A true coin the cosmos hasn't flipped. So Schrödinger couldn't be waved off with, well, the cat is really just alive or dead and we don't know which. He'd chosen the one trigger where the quantum fuzziness is real and unavoidable, and then wired it, step by pitiless step, straight to something the size of a pet. You cannot escape into ignorance. That was the whole design. Now, said Schrödinger, if you believe the equation applies all the way up from the atom to the whole box, then the honest quantum description of that sealed room, after 1 hour, is a cat that is equal parts living and dead, smeared together. His exact phrase for it, translated, is that the living and dead cat would be mixed or smeared out in equal parts. And his entire point was, that's obviously wrong. No one has ever seen a smeared cat. Cats are alive or dead. The fact that the theory, taken literally, produces a blurred cat is not a triumph. It is a symptom. It means we do not yet understand where the crisp, definite world of cats comes from, or where the fuzzy quantum description is supposed to stop. He was not saying, isn't reality amazing? He was saying, look at the ridiculous place my own theory leads, we have work to do. The cat was a diagnosis, not a miracle. Schrödinger built it to embarrass the fuzzy thinking of his day, and the internet turned his embarrassment into a mascot. And here's the strangest turn in the whole tale. For decades, almost nobody paid the cat much attention. Einstein and Schrödinger lost the public argument. The Copenhagen camp's practical recipe worked so well for building lasers and transistors and bombs that most physicists adopted a famous, unofficial motto, shut up and calculate. The philosophical worry got shelved. The cat sat in a footnote. It wasn't until the 1970s and 80s, when people finally built the mathematical machinery to describe how a quantum system bleeds into its environment, that the cat came roaring back not as a punchline anymore, but as the perfect mascot for a question we could finally attack with equations and, eventually, with lasers. Schrödinger died in 1961, never knowing his joke would become one of the most productive questions in modern physics. He wrote it to close a door. It opened. To see why Schrödinger's joke is so sharp and where he himself was missing a piece, we have to be honest about what superposition really is. Because the myth abuses that word badly. When people hear an electron is in two states at once, they picture a little ball that is somehow in two places, like a coin spinning so fast it's both heads and tails. That picture is wrong, and it's the root of the confusion. Superposition is not the thing is secretly in both states, and we just don't know which. It's stranger, and, oddly, more precise than that. A quantum system is described by a mathematical object, a wave function, that carries the full list of possible outcomes, each with a specific weight. And here is the part that makes it physics and not mysticism. Those possibilities can interfere with each other, add up, cancel out the way, ripples on a pond reinforce and flatten each other. That interference is measurable. It leaves fingerprints. It's not a story about our ignorance. It's a feature of the world that shows up in hard data. The cleanest place to see it is the double-slit experiment. Fire single particles, one at a time, at a barrier with two slits. Each one lands as a single dot, always one dot, never smeared. But let thousands pile up, and the dots arrange themselves into bright and dark stripes, an interference pattern. Each particle, somehow, went through the setup as a superposition of through the left slit and through the right slit, and those two possibilities interfered. Try to catch which slit it actually used, put a detector there, and the stripes vanish. The particle picks a side. The magic word for what killed the pattern isn't consciousness. Hold that thought. It's the whole key. And I need you to feel why that interference pattern is the whole ballgame, because this is the exact spot where the myth cheats. Suppose you insisted the particle was really only ever going through one slit, and we just didn't know which, a hidden fact, a coin already landed. Then blocking the other slit shouldn't matter to a particle that never went near it, but it does. Close one slit, and the stripes disappear. The particle lands in places it never landed when both slits were open. The pattern that appears with two slits has dark bands, spots where particles hit constantly with one slit open, and never hit with both. Adding a second path made certain outcomes impossible. There is no "it secretly went through one" story that produces that. The only thing that does is a genuine superposition of both paths interfering. That's why physicists don't treat superposition as a fancy word for ignorance. It leaves marks in the data that ignorance cannot fake. So, superposition is real, and it's not a metaphor. But notice what all our examples have in common. Electrons, photons, single atoms, tiny, isolated things. The genius of Schrödinger's cat was to ask the forbidden question, what happens when you chain a tiny, superposed thing to a giant, everyday thing? At what point in that chain atom, counter, hammer, flask, cat, does the fuzzy both turn into the crisp one? This is the real puzzle. Physicists gave it a name, the measurement problem. And here's the sharpest way to feel it, worked out by the mathematician John von Neumann. Follow the chain. The atom is in a superposition. The Geiger counter looks at the atom, so now, by the same math, the counter is in a superposition of clicked and not clicked. The hammer looks at the counter, so the hammer is in a superposition. The cat, the poison, the walls, the whole box, each thing that interacts just inherits the superposition and passes it up the line. Nothing in the equation ever says, stop here, collapse now. The math would happily smear the entire universe. So where does it end? When you open the box, are you now in a superposition of having seen a live cat and a dead one until your friend outside the lab opens the door and looks at you? The physicist Eugene Wigner pushed exactly this, and it's still called Wigner's friend. The chain has no obvious last link. That is the measurement problem in one sentence. The theory tells you how superpositions evolve, but never tells you when or whether one of them actually becomes a single fact. And I want to be completely straight with you. This is one of the places where honest physicists still disagree. And I'm going to give the main camps their fair hearing, because you deserve the real map, not a slogan. Camp 1 is the Copenhagen view I mentioned. Measurement is special. It collapses the wave function to one outcome, and you shouldn't ask what's happening underneath. It's the textbook default, and it works flawlessly for calculating. Its weakness is that it never defines, in physical terms, what counts as a measurement. Camp 2 is the many worlds interpretation proposed by Hugh Everett in 1957. Everett said, take the equation completely literally, never collapse anything. The superposition is real all the way up, which means when you open the box, the world genuinely splits, and there's a branch with a live cat and a branch with a dead one, each with a version of you. Nothing is added, nothing collapses. The cost is a staggering number of unseen worlds. Camp 3 is the pilot wave picture, from Louis de Broglie and later David Bohm, where particles always have definite positions. Guided by a real wave, the cat is always just alive or just dead, and the fuzziness is only in our knowledge. It's fully deterministic. Its cost is a frankly weird, faster-than-light guiding field. And Camp 4 is objective collapse, models like the one from Girardi, Rimini, and Weber, which add a tiny new physical process that genuinely collapses superpositions at random rare for a single atom, near instant for something cat-sized. That one is exciting because, unlike the others, it predicts slightly different experimental results, which means we can actually test it. 4 serious answers. No experiment has yet knocked all but one out of the ring. Anyone who tells you the measurement problem is fully solved is selling something. But, and this is what the myth never mentions underneath all 4 camps, one enormous piece of the puzzle has been filled in since Schrödinger's death. A piece that every one of those interpretations now has to include. A piece that tells us exactly why you will never ever see a smeared cat. That piece has a name too, decoherence. Here's the question Schrödinger couldn't answer in 1935, and it turns out to be the crack the whole thing pours through. A cat is not isolated. Every example of clean superposition we have, the electron, the photon in the double slit, works only because the object is exquisitely alone, cut off from the world. The moment a quantum system touches its environment, something happens that Schrödinger's generation didn't have the tools to track. To follow it, you need an idea worked out mostly in the 1970s and 1980s by physicists like H. Dieter Zeh and Wojciech Zurek. The idea is called decoherence, and once you get it, the cat stops being spooky. Watch. And here's the beautiful irony, the thing that ties this whole story into a knot. The mechanism behind decoherence is the exact thing Schrödinger himself named in 1935 entanglement. Remember, he called entanglement the characteristic trait of quantum mechanics. Well, when the cat touches the air around it, the cat and the air molecules become entangled, their fates get linked, just like Einstein's 2 spooky particles. Every air molecule that bounces off the cat walks away, carrying a little piece of the cat's state, entangled with it. And here's the crucial move. Once the cat's aliveness is spread out, entangled across a trillion air molecules and photons, flying off in all directions, there is no way, even in principle, to to bring those pieces back together to make them interfere. The superposition isn't gone, it's just been shredded across the entire environment, irretrievably. Schrödinger built the cat to expose a problem, and he had already, without knowing it, named the very thing that would resolve it. The characteristic trait of quantum mechanics turned out to be its own cleanup crew. Superposition survives only as long as the different possibilities can still interfere, as long as they stay, in the jargon, coherent. Think of it like two singers holding a perfect chord. As long as nothing disturbs them, the chord rings. Interference lives in that clean relationship between the parts. Now, let a crowd into the room. Every cough, every scrape of a chair, every stray echo bounces off the singers and carries away a tiny recording of which note each one is holding. The information leaks out. And here's the killer. The instant the environment knows which note is which, the chord can no longer interfere with itself. The superposition doesn't get destroyed by a conscious list. It gets diluted into the room, smeared across billions of tiny interactions until the bothness is spread so thin it's gone from anywhere you could ever measure it. Now count the crowd around a cat. A cat sits in a bath of roughly 10,000 billion air molecules, slamming into it constantly. Infrared photons pour off its warm body every instant it's glowing in the dark to any infrared camera. Each of those collisions, each of those photons, carries away a scrap of alive or dead. The environment measures the cat relentlessly, trillions of times over, before you get anywhere near the lid. So how fast does the smear collapse? This is where the numbers become almost violent. Zurich worked a now classic example. Take an everyday object about 1 gram, roughly a paperclip, and put it in a superposition of 2 spots, just 1 centimeter apart, at room temperature, about 27 degrees Celsius, 80 degrees Fahrenheit. How long does the bothness survive? Roughly 10 to the minus 23 seconds. Let me try to make that number mean something, because your brain will just file it under small and move on. 10 to the minus 23 of a second is to 1 second, as 1 second is to about 1,000 times the age of the universe. It is so fast that light, the fastest thing there is, crosses less than the width of a single atomic nucleus in that time. For a whole cat, far bigger and warmer than a paperclip, the number is even more absurdly tiny. And this is the answer to a question that might be nagging at you. If superposition is real, why don't we ever bump into it? Why doesn't your coffee cup ever hover in 2 spots? Why doesn't your car sometimes interfere with itself in the driveway? Now you know. It's not that big things are exempt from quantum mechanics, they absolutely obey it. It's that big things are so ferociously well measured by their own surroundings, every fraction of every instant, that any superposition they might have is erased before a single atom in your eye could register it. Quantum weirdness didn't skip the everyday world. The everyday world is drowning in it so thoroughly that the weirdness cancels itself into ordinary, dependable solidity. The table is quantum. It's just quantum in a way that has been averaged by the universe into a table. That is Schrödinger's answer, arriving 40 years too late for him to hear it. The cat is never in a living and dead superposition in any way you could observe, not because you looked, not because a mind reached in, but because the cat is a loud, warm, enormous thing constantly bleeding its state into the air around it. The universe collapses the cat long before you touch the lid. Decoherence turns the crisp both into an ordinary one or the other. We just don't know which, yet faster than any clock can tick. And decoherence does one more thing, subtle and gorgeous, that answers a question you might not have thought to ask. Why alive or dead? Why not some other pair, a cat that's half in, some blend of the two? Zurich's word for the answer is Einselection, environment-induced selection. It turns out the environment doesn't measure every possible property equally. It relentlessly probes position, location, where is the stuff, because that's what air molecules and photons actually bounce off. And so the only states that survive the battering, the states the environment leaves alone long enough to be stable, are the ones that look classical. A cat here, alive, a cat there, dead. Those survivors even have a name pointer states, because they're the ones a measuring pointer can actually rest on. The environment isn't just destroying the superposition. It's selecting, out of infinite quantum possibilities, exactly the small menu of sturdy, everyday, this or that, states that make up the world you live in. The classical world isn't the opposite of the quantum world. It's the residue the quantum world leaves behind after the environment has scrubbed everything fragile away. Notice what that does to the poster. It removes you from the center of the universe. You are not the magic ingredient. Reality does not wait for your eyes. The cat's fate was sealed in the plain, boring sense of already one definite thing, an unimaginably long time before you walked into the room. The mysticism doesn't survive contact with the physics. Now, I told you I'd be honest, so here's the fine print, said out loud. Decoherence explains why we never see superpositions of big things. It explains beautifully why the world looks classical. What it does not, by itself, fully settle is the deepest version of the measurement problem, why you get one specific outcome rather than the other, the last philosophical inch. Different interpretations still fight over that inch. But the thing Schrödinger found ludicrous, a cat visibly smeared between life and death decoherence, has genuinely put to rest. The burlesque cat is dead. What remains is a real, narrower, honest question. And that's not a step backward. That's what progress in physics actually looks like, a giant mystery shrinking into a small, sharp one. Here's the twist that would have delighted Schrödinger, and it's the part I love most. If superposition is real for small things, and decoherence kills it for big things, then somewhere in between there must be a frontier, a scale where you can build a genuine cat state, hold it still, and watch it decohere with your own instruments. And in the last 30 years, we've done exactly that. We built real Schrödinger cats, small ones, and we filmed them dying. Start with light. In France, the physicist Serge Haroche spent years perfecting a trap for photons, a pair of superconducting mirrors, chilled to near absolute zero, so perfect that a single particle of light could bounce back and forth inside for 1/10 of a second, traveling the distance to the moon and back without escape. Into that trap, he placed a tiny field of light coaxed into a superposition of two opposite phases, genuinely a mesoscopic cat, two states at once. And then, using single atoms as probes, Haroche's team watched, in real time, as the environment leaked in and the superposition faded. They didn't just theorize decoherence. They measured the clock on it. They watched the cat go from both to one. On the other side of the Atlantic, David Wineland, at the U.S. National Institute of Standards and Technology, did the mirror image feat with matter. He took a single ion, one charged atom, held it nearly motionless in an electromagnetic trap, laser-cooled it to a whisker above absolute zero, and split it into a superposition of two locations at once, separated by more than the atom's own width. A single atom, in two places, held open long enough to study. A Schrödinger cat you could point at. Stop and appreciate what that means, because it's easy to skate past. Schrödinger's whole complaint was that the transition from quantum fuzz to classical fact was invisible, a magic step the theory couldn't describe. Haroche made that invisible step visible. He built a cat small enough and isolated enough that its decoherence took not 10 to the minus 23 seconds, but long enough to clock, and then he took snapshots of it happening, watching the superposition drain away toward a definite state, frame by frame. For the first time in history, someone had filmed the quantum to classical boundary in the act. The thing Schrödinger said was a ludicrous black box we opened and photographed the machinery inside. In 2012, the Nobel Prize in Physics went to Haroche and Wineland together for methods that let us measure and control individual quantum systems without destroying them. For learning to hold a cat gently enough that it stays in superposition, and to watch, tick by tick, the exact moment the world reaches in and makes it choose. And this isn't just a museum piece to admire. The very skill that lets you hold a cat state steady, isolating a quantum system, shielding it from the environment, watching it without wrecking it, is the founding skill of the entire quantum technology revolution. Everything downstream of those experiments, from the atomic clocks that keep GPS honest, to the quantum sensors that can feel a single magnetic field, flipped to the quantum computers we'll get to in a moment, rests on the techniques Haroche and Wineland pioneered for babysitting fragile superpositions. Schrödinger's cat stopped being a philosophy seminar curiosity and became an engineering discipline, learning to keep the cat in the box, in superposition, a little longer than nature wants to allow. That is now a job you can have. And the frontier keeps climbing. The question, how big can a superposition get before decoherence wins, is now an experimental sport. In 2019, a team led by Markus Arndt at the University of Vienna took molecules built from up to 2,000 atoms, massive, floppy, Complicated things weighing more than 25,000 times a hydrogen atom sent them through an interferometer and got them to interfere. 2,000 atoms, each molecule going through as a superposition of paths, leaving the telltale stripes. 2,000 atoms is still unimaginably smaller than a cat. A cat is something like 10 to the 25th atoms. We are not sneaking up on live cats, but every one of these experiments is a stake driven into the map, marking how far up the quantum world reaches before the environment shuts it down. And every stake lands exactly where decoherence predicts. The theory that killed the burlesque cat also tells you precisely how hard it is to build a small one, and so far, it's batting 1,000. That's the reframe Schrödinger never lived to enjoy. His cat was supposed to be a reductio, an absurdity, so total it proved the theory couldn't mean what it said. Instead, the theory grew up, explained why his cat could never be seen, and then handed us the tools to build cats small enough to hold. The joke became a laboratory. So why should any of this touch your actual life, tonight, outside a physics building? Because decoherence, the cat's real killer, is the single biggest obstacle standing between us and quantum computers. A quantum computer's power comes from holding many superpositions at once and letting them interfere, exactly like the double slit but orchestrated. And its mortal enemy is precisely the thing that flattens the cat: the environment leaking in and measuring the machine before it can finish thinking. That is why the quantum computers being built right now sit inside golden cryostats, chilled colder than deep space, a few thousandths of a degree above absolute zero, colder than anywhere in the natural universe, shielded from every stray photon and vibration. Every engineer in that field is, quite literally, fighting Schrödinger's cat for a living. They are trying to keep a cat alive and dead just a little longer than the air will allow. And there's a twist here that closes the whole loop. Some engineers have stopped fighting the cat and started using it. There is a real cutting-edge approach to quantum computing built on what are literally called cat qubits, the idea, pioneered by the physicist Mazyar Mirahimi and colleagues in 2014, of encoding information not in a single fragile particle but in a superposition of two opposite states of a trapped microwave field. A genuine little Schrödinger cat state. Because of the peculiar shape of that state, one whole class of errors becomes exponentially rare, so the machine protects itself. In early 2025, Amazon unveiled a prototype chip named Ocelot built on exactly this principle, cat states, etched into superconducting hardware, doing useful work. 90 years after Schrödinger drew his cat to mock a theory, engineers are stamping tiny cats into silicon to build the computers of the next century. The insult became infrastructure. And there's a second thing, quieter and more human. The next time someone tells you that quantum physics proves your mind creates reality, that you manifest the world by observing it, that the universe is waiting on your consciousness, you can now hand them the truth, gently. The cat was never a mystic's parable. It was a physicist's protest. The thing that collapses the cat is not your awareness. It's a storm of dumb air molecules that were opening the box long before you arrived. Reality is not fragile, and it does not need you to look at it to exist. If anything, the real lesson is the opposite of the poster. The universe is robustly real, so aggressively real that it erases quantum fuzziness in less time than light needs to cross an atom. And I want to leave that last open question standing, honestly, because this is where a lot of science communication lies to you, and I won't. Decoherence tells you why the cat looks alive or dead and never a blur. It does not, all by itself, tell you why you, personally, open this particular box and find this particular cat dead rather than alive. Whether the other outcome simply doesn't happen, or happens in a branch of reality you'll never visit, or gets snuffed out by some collapse process we haven't yet detected that is still genuinely argued over by brilliant people, and I'm not going to hand you a fake certainty to tie a bow on it. What I can tell you is that the question has gotten sharper, smaller, and more testable every single decade. That is what an honest science looks like from the inside. Not a finished cathedral, but a boundary we keep pushing, one careful measurement at a time. I think Schrödinger would be at peace with where his cat ended up, not as a riddle about human minds, but as the exact spot where we learned to draw the line between the quantum world and ours. He built a joke to expose everything we didn't understand. 90 years later, that joke has quietly become one of the best understood boundaries in all of physics, with the honest, human admission that a final sliver of it is still open. That's not a defeat. That's the whole point of the enterprise, to take a ludicrous, hand-waving mystery and grind it, decade by decade, receipt by receipt, into a clean, sharp, half-answered question. That is what physics is for. Here's something you can do with this tonight. Find someone who's repeated the nothing is real until you observe it, line everyone knows one, and tell them the real story. Tell them the man who invented the cat was making fun of that exact idea. Tell them the air opens the box. Watch their face rearrange. That look the moment a familiar myth turns inside out and becomes something truer. That's the whole reason I make it. If you've ever felt talked down to by science, handed a slogan instead of a reason, told to just accept that the universe is weird, then you already understand why this channel exists. We don't do slogans here. We do receipts. So tell me in the comments, what's one piece of quantum weirdness you were handed as a fact that you now suspect is a myth in disguise? Name it. I read these, and the best ones become future episodes with sources. If a boundary you'd been afraid of just turned into something you can actually see, subscribe to the Physics Storyteller. Every video, we take one thing you thought you understood and show you the real machinery underneath. Next time, we open another box the culture got exactly backwards, and I'll show you the receipts, same as always. Because the universe doesn't need you to believe it. It just needs you to look closely. This has been the Physics Storyteller. Keep your hand on the lid. Stay curious.